So when we first started talking about energy, we said there were a couple goals that we have. The first is learning to recognize forms of energy. At this point in the course, we've talked about kinetic energy. We've now introduced potential energy. Later in the course, we'll talk about thermal energy. There are other courses where you might talk about electromagnetic energy or chemical energy or nuclear energy. But right now for us, we're going to focus on these first two, kinetic energy and potential energy. When we add those two together, the sum, kinetic plus potential, is the mechanical energy. So we can talk about the mechanical energy of a system as being the sum of the kinetic and potential energies of the system. And so the kinetic energy, right now we've got one, energy due to an object's motion. We calculate that as 1/2 mv squared. Potential energy, we said that's energy due to an object's position. And right now we have two, right? So there's the gravitational potential energy, which we can calculate as plus or minus mgh. So what is that relative to a 0 point? There's also the elastic potential energy, so 1/2 kx squared. So what is the elastic potential energy relative to the 0 point at equilibrium? The detail we can't ignore when we're dealing with these potential energies is that equation gives us a potential energy relative to some 0 point. So if you want to talk about the mechanical energy of your system, we need to be clear what the 0 point is so you can so that the potential energy terms are well defined. Our second goal was learning how to keep track of the energy of a system. And so we introduced the first way that we were going to do that by talking about the work energy theorem. Well, now that we've added this new idea of potential energies, let's come back and look at the work energy theorem and say we can take that work term and break it up into two pieces. So first there's the work done by conservative forces, that's this first term W sub C, plus the work done by non-conservative forces, that's the second term WNC. So this is the work done by conservative forces plus the work done by non-conservative forces. Again, add those together, I just get the net work acting on the system. So that still has to be equal to the change in the system's kinetic energy. But of course, we now know what the work done by conservative forces is related to. That's equal to negative the change in the potential energy. What we're seeing is that now that we can relate the work done by conservative forces to the change in potential energies, we can reframe the work energy theorem. And so all I'm going to do is break up this term, and since this is negative the change in potential energy, this will actually be the initial minus the final potential energy plus the work done by non-conservative forces equals, and delta K is just final minus initial kinetic energy. I'm going to choose to take all the initial terms over to the left, the final terms over to the right, and so what I'm left with is this expression that says the initial kinetic energy plus the initial potential energy plus the work done by non-conservative forces equals the final kinetic energy plus the final potential energy. And so this gives us a second way to keep track of the total energy of a system. Notice kinetic plus potential, again, that's just the mechanical energy. So what this equation tells me is that I can think about, or I can keep track of the energy of my system by thinking about the total mechanical energy it starts with, plus the work done by non-conservative forces. That's going to tell me the final total mechanical energy of my system.